Okay, hello everybody. So this is a little supplementary material to lectures on week 6, where we essentially defined for ourselves the concept of Lyapunov stability and conditions to verify stability in terms of eigenvalues and some other LMI like condition, like the A transpose P plus PA is minus Q and so on. In the proof of one of those, we had used something called the comparison lemma. So, I will do a small proof of that, and also in addition I will give you a little more physical interpretability of the solutions, especially of the condition 5 that we had for stability of which was like A transpose P plus PA is less than 0. So, essentially conditions which look like this. So, we will try to see if there is any physical interpretation to this condition number 3. Okay, so we will start with proving the comparison lemma. So, the statement I will read out again. So, given Vt which is a differentiable signal which satisfies a condition like this, that V dot t is less than or equal to mu V of t, then essentially V of t, the solution of it looks something like this. Okay, so I will just do a small proof of that, and it is sometimes useful to know how this proof techniques were derived. So, what are we given is V is a differentiable signal in such a way that V of t is equal is less than or equal to mu times V of t. This mu could be anything in R, and for some or for all times t greater than some defined initial time t0. So, if this holds, then V of t is less than or equal to e power mu t minus t naught V at t naught. Okay, this inequality was essentially useful in proving the condition, the fifth condition on the Lyapunov stability, namely A transpose P plus PA is less than 0. Okay, so we will do a little proof of this. Okay, so what does the proof say? Okay, let us define a new signal u of t, which looks like this. U of t is e power minus mu t minus t naught V of t, again for all times t greater than or equal to t naught. Okay, so I will just take the derivatives on both sides. This will be u dot t is minus mu e power minus mu t minus t naught V of t plus the same thing as e power minus mu t minus t naught V dot of t. Okay, what do I know of V dot of t? So, V dot of t is satisfies this is actually given to me. So, this will be less than or equal to minus mu e power minus mu t minus t naught V of t plus e power minus mu t minus t naught. What is V dot? V dot is mu V of t. So, this is equal to 0. Okay. So, what do we know that? So, u dot is equal to 0. This means that u is non increasing. Right, and therefore, u of t is, which is, this is how we defined it, right, e power minus mu t minus t naught V of t starting from here. Okay. So, this is less than or equal to the value of u at t naught. Okay, now what is the value of u at t naught? Just substitute for t naught here, u of t naught is e power minus mu t naught minus t naught times v at t naught. So, u at t naught, so this goes to 1, now this is v at t naught. Okay, now take a look at this. So, what do I have? E power minus mu t minus t naught, v of t is less than or equal to v t naught. Okay, this is essentially what I wanted to prove, right. So, I can just rearrange and write this as the following. Right, and this is what we wanted to prove, and this concludes the proof. Okay. So, it is a very nice intuitive proof here, and of course, we saw how this was instrumental for us in deriving stability conditions for linear systems. Okay. Now, so if I can go back to this thing here, the equation number 3, this essentially, so how did the proof go? The proof required defining a scalar signal v of x t as x transpose p times x t. It is a quadratic function which is always greater than or equal to 0, and we showed that the time derivative of v dot or the time derivative v dot was less than or equal to 0, or which also had some bounds, and therefore, since v dot was less than 0, v was converging exponentially fast, and so does the solution. Okay, so what does this mean in terms of does this have any physical interpretation? Right. So, again we start with the autonomous LTI system, x dot is a x of t. Okay, and then we had this condition A transpose P plus PA is less than 0. Not only that, we defined a function v as v of t is x transpose Px, and then we were interested in the time derivatives of v. Of v, right. So, we computed v dot and then derived a bunch of properties based on the system dynamics, based on this condition, and what we showed essentially that this condition satisfaction of this condition was actually equal to or actually implied exponential stability. Okay. So, if we digress a bit and then we look at some literature from how do they prove stability in the nonlinear case. The first one is what they call as the first method of Lyapunov. And this essentially involved linearization of the nonlinear system of what we saw, right. So, stability, so we start with a nonlinear system, x dot is f of x, we have some linearization delta x dot is a delta x, and stability of A had some direct implications on the stability of x dot is f x. Again, this is all around an equilibrium point. Of course, we here rule out the condition when A has a 0 eigenvalue. A counter example to that was x dot equal to x cube and x dot is minus x cube, which both had the same linearization, namely x dot is 0 and x dot is 0, and we could not say anything about the stability of the nonlinear system. Okay, so that is that we dealt with quite extensively. There is also something called the second method of Lyapunov. We will not analyze this thoroughly in the context of nonlinear systems, but we will try to interpret that in our within the context of linearized system. Okay, so I start with this dynamics x dot is Ax, right. So this could be linearization of a nonlinear system around an equilibrium point and so on. So let V of t be, so this is a positive definite function x transpose p x. So this is usually in the nonlinear setting we will say we will define it. So this function is defined in a small neighborhood around the equilibrium point, but in the linear setting, well, we can assume it to be if it's the system is linear by nature, we can assume it to be valid for all x. Okay, so if x star is an equilibrium, okay, let us say x star is an equilibrium point. So the theorem says that x star is stable, or if I am looking of a nonlinear system, I am just looking at locally stable. Locally stable because nonlinear systems could have say isolated equilibrium points where, for example, this could be stable, this equilibrium could be stable, this could be stable and so on. So, I am just looking at its behavior around an equilibrium point within a small neighborhood, and therefore, I call it locally stable. This is not globally stable because all trajectories, if the trajectories start here or here, they may not necessarily converge to the origin, or even at this point, right, at this equilibrium if I start and so on. Okay. So, this system is stable if I am looking at this quantity dV by dt x of t, which is dV by dx times x dot. Okay. Okay, just put a little transpose here. If I just say this, I am just taking the gradient of this vector. If this quantity is less than or equal to 0, then the system is locally stable. Second, so x star is asymptotically stable if, okay, I will call this condition A, if A holds and the largest invariant set under this linear systems. I will, okay, let me call this LTI. Under this dynamics of LTI systems contained in the set. So, let me define a set W as all x belonging to some to the state space such that V dot of x t equal to 0 equals x star, right, which means that the only solution that starts in this set remains in W for all sets, right, and that actually coincides with the equilibrium point. Okay, so we will slowly see what this means in the context of some physical systems too. Okay, so let us take the case of a simple pendulum. right. So, and say just look at the linearized version of this. So, its dynamics around this equilibrium point x equal to 0 with no damping would look something like this, right. X1 dot is x2 and I normalize all parameters to be 1, x2 dot is minus x1. Okay. Now, how does the phase space of this look like? The phase space of this looks like this. So, it just concentric circles around the origin. So, here my origin is the equilibrium point, or here or here or here. Okay. Additionally, if I now define this function, right. So, v of t, so let me call this half x1 square plus x2 square. So, this is exactly this function with p being the 1 by 2, 0, 0, 1 by 2, and this you can see is symmetric and greater than 0. Okay. Right. So, this if you has also the interpretation of the total energy of the system, the kinetic energy plus the potential energy, like half mv square and half kx square kind of stuff. Okay. So, this is the total energy of the system. Now, when I say v dot dv by dx, sorry, dv by dt of x of t, so I am computing this quantity, right, dv over dx times x dot. So, what does this mean? So, what is dv over dx? If I just take the gradient of this, so I will get x1, x2, and here I have x2 and I have minus x1. This essentially is 0. Okay. So, what does this mean if I look at just this quantity, which is the definition of energy, that the rate of change of energy is constant, right, that the energy does not change with time. That is also okay from the physical interpretation, right. If I just have a lossless pendulum and I subject it to some initial condition, it will just keep on oscillating infinitely. Okay. Now, I can also look at it from the phase space, right, just take any point in the phase space. So, just take one initial condition, say over here, and this is how the trajectory will go, right, in the circle. So, at any point here, if I compute the energy here, it will be the same as computing the energy at this point or this point or this point. Why? Because even if I look at the solutions will be of the form x1 square plus x2 square is constant. Okay. So, that also is consistent with the phase space, right. So, this will give me tell me that this function x1 square plus x2 square is constant along the system trajectories. So, this is x1, this is x2, right, and therefore, the v dot is 0. Now, a third interpretation, right, of so this essentially can be looked upon as dot product of two vectors. So, how does a gradient vector look like? If I were just to plot, this gradient vector will simply look like this, right, something like this, something like this, something like this. So, essentially if I look at the so if I just zoom in over here, so the gradient vector will be something like this, okay, and the original phase space of the system will be just perpendicular to it in such a way that the angle between these two is 90 degrees, right, and then well, they are like perpendicular to each other, and therefore, the dot product will be 0, right. So that's another interpretation of it, right. It's the gradient of the energy function times the phase plane or the vector field of the system, how it looks like. Okay. Now, the second thing here is to do with asymptotic stability, right. So, what does the theorem say? That additionally, so let us say I take a system which is now like this, x1 dot, x2 dot, I just add some friction term or some damping term 0, 1, minus 1, minus 1, 0 and x1 and x2. Okay, now if I again look at V as half x 1 square plus x 2 square, I compute V dot, that is x 1 times x 1 dot plus x 2 times x 2 dot. So, this will be so x 1 dot is x 2 plus x 2. What is x 2 dot? X 2 dot is minus x 1 minus x 2. So, this is minus x 2 square, and this is less than or equal to 0. Okay. So, the statement says that well, the system is stable as long as dV by dt is either less than or equal to 0. So, in this case it was just equal to 0. Okay. So, this also means that so this statement A here, the condition A means that your solutions are uniformly bounded. That is the first condition we check for stability. Second condition we check for stability is that first, that the system should be stable, and it should also be in such a way that as t goes to infinity, the solutions go to the equilibrium point, which is the origin in this case. Okay. Now, why is this step here important? Okay. So, okay. So, what am I looking at? I am looking at the largest invariant set such that V dot equal to 0. Okay. What does it mean by V dot being equal to 0? V dot being equal to 0 implies I am looking at x 2 being equal to 0. Okay. And in turn also, if x 2 is 0, also have a x 1 is also equal to 0. Okay. So, what is, and why am I obsessed with the largest invariant set, right? So, here the statement says that the largest invariant set such that V dot equal to 0 should only be the origin, which is 0 comma 0 in this case. So, in this case the only possibility for V dot being equal to 0 is x 1 is x 2 equal to 0. Okay. Okay. So, why is this important to check this this additional condition? Why am I actually calling it the largest invariant subset? Now, if I go to the previous example where I had no damping, x 1 dot is x 2 and x 2 dot is minus x 1. What do I have is well, my phase plane is something like this. Okay. Now, what are the points or what are the set or what is the set such that V dot equal to 0? Now, I see that okay, at this point V dot is 0, at this point V dot is 0, at this point V dot is 0, this point also V dot is 0, this point also V dot is 0. If I start with this initial condition, so at each point in this curve the V dot equal to 0 in the x 1 x 2 plane, and therefore, this system, even though V dot is less than or equal to 0, is not asymptotically stable, because additionally I need to verify a condition like this, right, that the largest invariant set such that V dot equal to 0 is only the origin, which is actually happening in the second case, right. When V dot equal to 0, that means x 2 equal to 0. If I plug it in here, I get x 1 also equal to 0, and the only possibility here is x 1 equal to x 2 equal to 0, which is exactly my equilibrium point. Okay. Now, in the okay, that was about why we are obsessed with the largest invariant set. Now, if I look at the phase space in the second setting where I have some damping in the system, the phase spaces usually are the ones which go to the origin in the x 1, x 2, right, this So, possibly in this direction. So, they will spiral to the origin again based on what their eigen values are, if it is a stable focus and so on. Okay. So, if I now what happens to this function half x 1 square plus x 2 square, which essentially is the total energy of the system. At this point it has a certain value, and at this point the value diminishes, it diminishes further here, further diminishes here until it actually reaches to 0. So, from calculus this also means that V dot is less than 0 and V dot is equal to 0 only at x star. Okay. Now, the third condition, right, of an unstable system. Unstable system, okay, if you are looking at a saddle point, then this is how my phase space will look like. Or if I have say in some cases it might just spiral away from the origin, right, with this direction of the arrows. Okay. Now, what happens to the energy? Well, at this if I start slightly next to the origin, then you see that the energy, the value of half x 1 square plus x 2 square, it increases in and becomes unbounded, right, here also here, right. So, so stability can also in a way be interpreted as a certain energy function decreasing along the trajectories of the system and eventually going to 0. So, when my pendulum is swinging, it switches between its kinetic and potential energies, and at some point of time if there is dissipation, the energy will all dissipate and just go to 0. You can also talk of it in terms of an electrical circuit, of an RLC circuit. The energy will oscillate between the electric and magnetic part, and from the R will keep on dissipating the energy until it reaches the state of 0 energy. Instability will amount to the energy growing unbounded, at least mathematically. Physically, well, you will have some physical limitations that the energy cannot grow to infinity. Okay. So, that is the little interpretation of the Lyapunov stability in terms of the physics of the system, and that is what the motive of this entire supplementary material was, to actually give a little relation between stability and the loss of physics, which essentially comes from the loss of conservation of energy. And I hope this explanation was useful to you, and it will be more useful when you even do the nonlinear setting of Lyapunov functions. Thanks.